For half a century, the name Ton 618 echoed through the dark, a quasar so immense it could erase night itself, a monarch crowned by gravity and silence. But now from the southern edge of the cosmos, something stirs. Phoenix A, brighter, heavier, impossibly young. Its mass bends the language of physics, its light burns against the laws that should contain it. 2 black holes, 2 hearts of collapse, 1 throne. So close your eyes and prepare yourself. For tonight we will follow the light into the dark space to find who truly the king of black holes. Beyond the reach of every probe and the last pulse of radio light, a region of deep space glows faintly in X-rays like the scar of an old collision that never healed. Astronomers call it the Phoenix Cluster, and within that cluster lies a heart of gravity so immense it bends the language we use to describe it. They named it Phoenix A. It is not a star nor a galaxy, but a black hole of almost unimaginable weight, perhaps 196 billion suns pressed into a single invisible sphere. Around it, light itself seems to hesitate. From the frozen plateau of Antarctica, the South Pole telescope first caught its whisper, a shimmer of radiation hotter and brighter than any known core. What the instruments revealed was a furnace 10 times the energy output of the Milky Way, a gravitational engine swallowing matter at the rate of several suns every year. The data were clear yet absurd. Nothing in our equations predicted a black hole of this scale, not in a universe only 13 billion years old. Imagine standing somewhere inside that cluster far beyond the Milky Way. Galaxies would drift around you like glowing reefs, their arms coiling in slow motion. Between them, rivers of plasma flow like wind across an ocean made of darkness. Each current carries debris from ancient supernovae, feeding the invisible monarch in the center. You would not hear the sound of this feeding, only the vibration of it, a pressure in the chest, a resonance in the bones. The silence of Phoenix A is heavy, almost musical. To understand its scale, consider this: the event horizon alone would span 600 billion kilometers, a circle so wide that light would need more than 3 weeks to cross from one side to the other. If the black hole replaced our sun, its edge would engulf every planet and still stretch halfway to the nearest star. Around that abyss spins a disk of incandescent gas glowing blue-white at tens of millions of degrees, producing jets that shoot thousands of light years into the void. Every photon that escapes is a survivor carrying the memory of matter that once existed. Scientists describe this region as a balance of destruction and creation. As the black hole consumes, it also ignites new stars in the surrounding gas. Each year, hundreds of newborn suns flare into being around the cluster's center like sparks from a forge that never cools. This paradox fascinates physicists. How can something so violent become a cradle of light? The equations of accretion and feedback suggest that gravity and radiation are locked in a perpetual conversation, each restraining the other like dancers bound by the same rhythm. Still, the mystery deepens. How did Phoenix A grow so enormous in so little cosmic time? The most accepted theory suggests that it began as a direct collapse black hole formed when a primordial cloud of hydrogen collapsed under its own gravity before the first stars were born. Others propose a chain of mergers, hundreds of smaller black holes fusing over eons, each collision sending waves of gravity rippling through space-time. If those ripples were sound, the universe itself would be humming with their echo. Some even speculate that in the early epochs the laws of physics bent differently. Density and time intertwined more tightly, allowing giants to bloom faster than logic should allow. Perhaps beyond the veil of observation, other titans like Phoenix A still wait silent, invisible, older than our theories. We see only those that shine, not the ones that sleep. Our telescopes, however powerful, capture a fraction of the cosmic truth like lanterns, trying to map an ocean by tracing its foam. And here, beneath all calculation, something human remains. We look upward and measure, yet what we seek is not only mass or distance, it is meaning. To gaze at Phoenix A is to confront the idea of limit itself. How large can existence become before the universe resists? How heavy can darkness grow before it breaks the stage on which it stands? Take a slow breath. Imagine the entire solar system drifting through that cluster, like a grain of dust drawn toward the faint heartbeat of gravity. Somewhere ahead, the light bends curves and disappears, yet the pull continues. The mind follows quietly. The heart slows. And in that stillness, one question remains. If gravity has no ceiling, does creation ever truly end, or does it dream of becoming infinite? The last question lingers like an echo in deep space, and as that echo fades, the data begins to speak. Numbers, frequencies, wavelengths, each one a whisper of what truly lies within the Phoenix cluster. At first, astronomers doubted their own measurements. The signal was too strong, too hot, too large. Yet every recalibration led to the same conclusion, a gravitational monster far beyond the scale allowed by theory. In 2011, the South Pole Telescope recorded a pattern of X-ray intensity that pulsed like a heartbeat through the cosmic background. It was not a single source, but a roar of energy spreading across hundreds of thousands of light years. The core of the cluster shone brighter than 1,000 galaxies combined. Soon after, the Chandra X-ray Observatory joined the observation. Its instruments traced ribbons of gas spiraling inward plasma, heated to nearly 70 million degrees Kelvin. Each particle, once free between galaxies, was now caught in a gravitational storm spinning faster, hotter, closer. The data showed shock fronts rippling waves that revealed pressure changes in the intergalactic medium. To scientists, these patterns were the fingerprints of an accretion disk operating at full fury. Imagine standing at the rim of that disk. The light would not appear as light, but as motion torrents of brightness folding into darkness. You would see colors no human eye could name, the ultraviolet fury of gas torn apart and reborn as radiation. Each second, matter weighing more than Earth falls into the void. Each second, jets of energy burst outward at nearly the speed of light. The scale defies imagination, yet the data remains cold, precise, undeniable. To visualize the distance, take a thought experiment. If the black hole were placed at the center of our solar system, its event horizon would swallow Mercury, Venus, Earth, and reach well past Neptune. The sun itself would be nothing more than a flicker swallowed by the horizon's edge. We're speaking of gravity so powerful that not even light, that loyal courier of the cosmos, can escape. The Spitzer Space Telescope, sensitive to infrared light, added another layer to the puzzle. It detected waves of star formation surrounding the cluster's center, nearly 500 new stars every year. This contradicted the usual expectation. Supermassive black holes suppress star birth through violent winds and radiation. Phoenix A instead seemed to do the opposite. It devoured matter, yes, but somehow triggered creation in the chaos it left behind. For scientists, it was both miracle and paradox, a riddle wrapped in plasma. You can almost picture it, the black hole at the center, acting like a cosmic forge, turning the wreckage of galaxies into newborn suns. Around the maelstrom, clouds of hydrogen shimmer, condense, ignite. Each new star burns for millions of years, sending its own light back toward the abyss that birthed it. Creation and destruction dance in the same rhythm, like breathing: inhale, exhale, collapse, flare. Data from XMM Newton confirmed the pattern. Concentric rings of heat, shock, and radiation expanding outward. Computer simulations tried to reproduce it, but every model failed to sustain such growth without breaking known physics. The researchers recalculated accretion rates, adjusted feedback mechanisms, even proposed exotic dark matter influences. Still, the numbers defied them. It was as if Phoenix A were rewriting the rules of how energy organizes itself. Take another breath. The story deepens with the James Webb Space Telescope, which in later years peered into the cluster's infrared glow. It captured faint spectral lines, chemical signatures of elements, forged in ancient supernovae now being recycled in the accretion disk. Oxygen, iron, silicon, the bones of dead stars swirling back toward annihilation. These traces told scientists that Phoenix A had been feeding for billions of years, uninterrupted, an appetite that never paused since the dawn of structure itself. But the numbers do more than inform, they challenge imagination. The black hole's luminosity reaches 1047 ergs per second, equivalent to the energy of 100,000 supernovas exploding simultaneously. Yet this blinding output does not tear the cluster apart. Instead, gravity bends the radiation, folding it into elegant arcs. Space and light negotiate their balance like two ancient partners refusing to let go. From such evidence, astrophysicists derived a startling insight: the Phoenix cluster may represent a transitional phase, a cosmic laboratory where matter and gravity test the limits of endurance. Here the ratio of mass to energy approaches the edge of theoretical stability. Beyond this threshold, feedback loops of heat and radiation would normally halt further growth, the so-called Eddington limit. But Phoenix AI seems indifferent. It continues to feed its disk, pulsating like a living organism that has discovered how to cheat its own biology. Speculation follows like shadow after light. Could it be that inside its horizon, time itself stretches differently, allowing the black hole to experience growth at a rate invisible to our frame of reference? Perhaps what we perceive as billions of years is, from its perspective, a single sustained breath. If the universe expands, perhaps the black hole contracts in rhythm, balancing the equation of existence. Such thoughts are dangerous yet irresistible. Every generation of astronomers meets one discovery that forces them to question the foundations of everything before it. Phoenix AI is that moment for us. It whispers that there may be a deeper geometry beneath physics, a symmetry between creation and collapse we have only begun to sense. And still, after all calculations, there is humility. We look through the cold data and feel something warm awe, because behind every number lies a question that is almost human. How far can reality stretch before it tears? How much can the universe hold before it decides to fold back into itself? You can close your eyes now and see the data not as lines and digits, but as light billions of photons traveling across eternity to reach our fragile detectors. Each one tells us that truth, even when silent, is alive. It moves, vibrates, calls us closer. The truth of Phoenix A is still unfolding. The measurements continue, the models evolve, and with each refinement the mystery grows deeper. We are not chasing certainty, we're tracing the outline of wonder, and from within that wonder another question rises, quiet, gravitational, impossible to ignore. If this is what we can measure, what waits beyond what we cannot? From that thought begins the next chapter, where data gives way to rivalry, and the universe crowns another contender for the throne of darkness. The universe rarely accepts a single throne. For every crown placed, another contender rises from the dark. As the story of Phoenix A spreads through observatories and late-night data labs, a second name returns from the archives, TON 618. For decades it has ruled as the monarch of mass, a quasar so bright it once defined the upper bound of cosmic power. Now the two giants face each other across billions of light years like ancient empires separated by time instead of distance. When scientists first compared their figures, the rivalry felt almost poetic. TON 618, discovered in 1957 through radio signals bouncing off the ionosphere, carries a mass of about 66 billion suns, a figure that once seemed absurdly large. Its quasar core burns with such ferocity that if it replaced our sun, its glow would outshine the Milky Way and erase night from every sky. For half a century, textbooks cited it as the largest known black hole, the archetype of cosmic excess. But Phoenix A, younger and more elusive, arrived like a whisper turned into thunder. If its estimated weight of 196 billion suns holds true, the cosmos has rewritten its hierarchy again. Imagine both objects suspended in the same mental frame, two whirlpools in the sea of space-time. Around each matter spirals inward, breaking atoms, releasing jets of light. Their disks blaze with temperatures of tens of millions of degrees. Their magnetic fields twist like knots of lightning. Yet their personalities differ. TON 618 is a performer brilliant and loud, a quasar that announces its presence across the spectrum. Phoenix AR is the recluse buried in the dust of its cluster, glowing mostly in X-rays and silence. One shouts, the other broods, both reshape the space around them. The rivalry is not merely a contest of size, but of interpretation. Some astronomers argue that measurement bias makes Phoenix A appear heavier than it is. Others suspect that TON 618's distance and redshift distort its calculated mass. Light, after all, is a tricky messenger. It stretches as the universe expands, losing the truth of its origin. Our instruments catch only echoes, and each echo must be translated through theory. Still, even with uncertainty, both black holes sit at the very edge of possibility, near or beyond the limit that physics once set as sacred. Picture for a moment what these numbers mean. A black hole of 100 billion suns possesses a gravitational radius larger than the orbit of every planet in our solar system. The light we see from TON 618 began its journey more than 10 billion years ago when Earth itself was still molten. Phoenix A shines from a distance so immense that the photons reaching us tonight began their voyage before galaxies took their present form. When you look at either object, you're seeing the past outshining the present, the memory of violence turned into beauty. Between the two lies not competition but continuity, a lineage of collapse. Every supermassive black hole is built from smaller ones merging, consuming, merging again. Somewhere in the deep cosmic past, the ancestors of Phoenix A and TON 618 might have shared a similar birth, vast clouds of hydrogen collapsing, without forming stars, their centers becoming singularities that would never stop feeding. Each merger released gravitational waves, ripples still passing through space, brushing against the detectors of LIGO and Virgo like faint drumbeats of an ancient war. In laboratories on Earth, computers attempt to recreate this evolution. Simulations run for weeks, mapping collisions between galaxies, tracing flows of dark matter. The digital universe blooms, collapses, and blooms again. Yet even in the most advanced models, black holes rarely reach such magnitudes. Something in reality accelerates growth beyond the equations, perhaps magnetic reconnection, perhaps the geometry of space-time itself, aiding the fall of matter. Each new discovery adds not clarity but depth to the riddle. For the scientists who live with these numbers, the rivalry of giants becomes personal. They meet at conferences and argue over datasets, over luminosity curves, over calibration constants. A few defend on 618, like historians protecting an ancient dynasty. Others champion Phoenix A, the rebellious newcomer from the southern sky. And beneath the debate lies a quiet admiration, the recognition that both objects in their enormity remind us how small the field of human certainty truly is. If you step outside on a clear night and look upward, both black holes are invisible, yet their influence hums beneath the stars you see. The light of every galaxy you can name has passed near some greater darkness. Gravity sculpts beauty and competition fuels curiosity. Through rivalry, understanding grows. Now imagine drifting between them across the invisible bridge of cosmic scale. You would pass clusters, filaments, empty voids larger than imagination. The background radiation would fade to a low hiss. Even time would feel slower, stretched thin between two colossal attractors. You might not know which direction leads forward. Gravity itself would decide. Somewhere Phoenix A continues to feed. Elsewhere, Ton 618 burns in its luminous solitude. Both rule, neither yields. Perhaps the universe prefers it that way, balanced through opposition. And as the data of both giants continues to refine, new contenders stir in the catalogues objects like S5, 4001, Holm 15A, OJ 287, each one whispering of another record yet to fall. The throne of darkness has no permanent king. It passes from discovery to discovery, from light to absence. The astronomers record the numbers shift and all remains constant. Take one slow breath. Let the thought settle that somewhere far beyond the rim of our galaxy, colossal hearts of gravity beat in unison, unseen yet eternal. The rivalry of giants is not a story of conflict, but of inheritance. And from that inheritance rises the next question. Carried on the hum of plasma and time, if two such monsters can exist, what else is waiting in the uncharted depths between them? The rivalry fades behind us like twin echoes in the dark. And from that silence, a new question stirs, not about the giants themselves, but about their birth. If two such colossal beings now exist, what was the seed that allowed gravity to dream this big? Astronomers trace the story backward, rewinding the cosmic film to the first billion years after the Big Bang. The young universe then was a fog of hydrogen and helium. No stars, no galaxies, only gas shimmering at the edge of transparency. It was a time before light had a direction, when gravity began sculpting structure out of chaos. Somewhere in that haze, the first black holes may have appeared small as stars or vast as galaxies, depending on how the dice of matter fell. We know that ordinary stellar black holes form when massive stars collapse at the end of their lives. But the earlier stars, the so-called population 3 stars, were giants, beyond comparison hundreds of times heavier than the Sun. When they died, they left behind remnants of unimaginable density. If those remnants merged quickly, they could become the first seed black holes, the ancestors of every supermassive one that came after. It is possible that Phoenix A began as such a seed hidden in the heart of a proto-galaxy that no longer exists. Yet the data whispers something stranger. Even the most aggressive merging of stellar black holes cannot reach billions of solar masses so early. The universe simply hadn't lived long enough. So scientists proposed a new mechanism: direct collapse. In this model, a vast cloud of pristine hydrogen, millions of times heavier than the Sun, skipped the process of forming stars altogether. The cloud fell inward under its own weight, compressing until the laws of physics surrendered, and a black hole was born fully grown, as if the universe had taken a shortcut. Imagine standing there, if there could even exist at the moment the first light condensed into darkness. Around you, the air of space would tremble. Gravity would hum like a deep note through the void. The newborn black hole would be silent, yet the surrounding gas would ignite into a halo of heat, brighter than anything that had come before. In that instant, the universe learned a new trick to create by collapsing. Simulations of this process show that under the right conditions, low metallicity, high density, and minimal turbulence, a direct collapse black hole can reach a mass of 100,000 suns in a single event. From there, it could grow rapidly, feeding on the gas around it. If enough matter funneled inward, the sea could bloom into a billion solar mass colossus within a few 100 million years. This is not a fantasy. It is a window into the logic of cosmic efficiency. To imagine how it works, think of a vast whirlpool forming in a boundless ocean. Each wave that falls in adds to its strength. The heavier it becomes, the faster it grows, drawing currents from farther away. At some critical moment, the whirlpool is no longer just a disturbance. It becomes the ocean's own heartbeat. Phoenix A, Ton 618, and all their kin may have begun as ripples that learned how to keep collapsing. Data from the James Webb Space Telescope are beginning to test this theory. By peering into galaxies more than 13 billion light-years away, Webb has found quasars already active when the universe was less than 5% of its current age. Each one requires a supermassive black hole at its center, far too large to be explained by ordinary stellar evolution. This supports the idea that direct collapse seeds were not rare exceptions, but a natural phase of cosmic growth. The early universe in its youth may have been a factory of black holes, bright furnaces briefly flaring before fading into silence. Still, questions multiply. If such seeds formed easily, why do we not see more remnants of them now? Did some remain small, hidden in dwarf galaxies, while others consumed their hosts and vanished into the background radiation? And could there exist a bridge between direct collapse and stellar merging, a hybrid path that combines both stories? Science thrives on these gaps. Every uncertainty is an invitation to explore. Close your eyes for a moment and imagine the scene billions of years ago. No stars yet, only a slow glow across an endless horizon. Then in one corner a shimmer, a tremor, a region where gravity decides to gather itself. Atoms drift closer, faster, until the entire cloud folds inward. The collapse is silent, but if you could hear it, it would sound like a deep rolling breath. When the pressure exceeds the strength of the atoms, everything gives way. A singularity forms, invisible but absolute. Around it, light blooms like the first heartbeat of creation. That was the beginning, the birth not of a star but of a law, the universe's own tendency to fall inward. From that moment onward, every galaxy carried within it a reminder at its center, something ancient still hungers. Phoenix AA is only the latest heir to that hunger, the distant descendant of those first collapses. When we look at it today, we're not just witnessing an isolated phenomenon, we're glimpsing the memory of the cosmos learning how to organize itself. Perhaps the truth is simpler and more profound. Maybe the seeds of black holes were inevitable gravity's answer to expansion. As the universe stretched outward, it also needed anchors, points of impossible density to balance the drift. In that balance lies harmony, and in harmony, endurance. The giants we know now, the rivals, the kings, the unseen masses sleeping between galaxies, all trace their lineage back to that first compromise between light and gravity. To study them is to study the heartbeat of creation itself. Take another breath. Feel the weight of that first collapse, the slow rhythm that still pulses through space. Every time a star dies, every time matter falls inward, the universe remembers its own beginning. And from that remembrance, a new question takes shape, quiet but insistent if such seeds were possible. Once could they still form today, hidden somewhere beyond our sight, preparing the next generation of giants? The last thought drifts like mist over an ancient ocean, and then movement. From the stillness of the first seeds comes the flow, the eternal current that nourishes every black hole. The universe does not stop at creation, it begins to feed. Astronomers call this process accretion, the slow, relentless falling of matter into gravity's mouth. It is the bloodstream of galaxies, a circulation of gas dust and broken starlight, spiraling toward the centers of worlds. Every photon, every atom carries with it the memory of a journey through time. Wherever there is density, there is drift, and where drift becomes surrender, a black hole begins to grow. For Phoenix A, that river of matter is colossal. Observations show clouds of hydrogen, tens of millions of light-years wide, streaming toward the cluster's core. Temperatures rise to tens of millions of degrees, atoms stripped naked by shock and radiation. The material forms an accretion disk, a ring of plasma so bright it could outshine entire galaxies, yet so turbulent that light itself is bent into spirals. Superheated iron emits X-rays rippling through the void like invisible surf. These ripples, detected by the Chandra and XMM Newton observatories, sketch the anatomy of the flow turbulence compression collapse. Imagine it from within. You're a particle of dust born in a dying star. For eons you drift through intergalactic darkness, until one day you cross an invisible boundary. Gravity seizes you, a silent invitation you cannot refuse. You begin to fall not straight, but in circles, faster and faster. The universe spins around you like liquid fire. Time stretches. You become heat-light energy, and then you vanish, joining the heartbeat of the giant below. Scientists model these movements using the equations of general relativity and magnetohydrodynamics. They simulate billions of interactions, gas streams colliding, magnetic fields, twisting shocks transferring angular momentum. In those digital universes, patterns emerge beautiful, terrifying. Matter does not simply fall, it dances. Every filament of gas curls like smoke drawn toward a candle flame, feeding the singular point that defines the cluster's rhythm. The rate of this cosmic feeding is extraordinary. Data suggests that Phoenix A consumes the equivalent of 60 suns each year, a banquet unmatched in the modern universe. To grasp the scale, imagine 60 stars like ours disappearing annually, their essence converted into radiation and gravitational waves. No city, no civilization, no epoch could measure such appetite. It is both destruction and renewal, the very mechanism through which galaxies evolve. The process is not smooth. Accretion is a storm. Magnetic turbulence triggers eruptions, sending relativistic jets thousands of light years outward. These jets carve cavities in the surrounding gas, visible as voids in X-ray maps. Ironically, these explosions also seed new stars. The shockwaves compress cold clouds in the cluster's outskirts, igniting future suns. Thus the river feeds both ends of existence, into the mouth of darkness and into the birth of light. To the human eye, it might look serene, but the math tells another story. Inside the disk, particles orbit at half the speed of light. Temperatures climb to hundreds of millions of degrees. Time dilates so that a single minute near the horizon might equal 1,000 years outside. If we could observe a single grain of dust falling into Phoenix A, we would watch it freeze in slow motion, forever suspended at the edge of the visible. Its final plunge would never reach our eyes. Light itself would never return to tell the tale. Speculation blooms where observation ends. Could this river be endless? Some models suggest that black holes once large enough attract matter, not just from their immediate surroundings, but from the cosmic web itself, those vast filaments of dark matter connecting clusters across billions of light years. If Phoenix A sits at such a node, then every motion of the universe above it, every fluctuation in density eventually flows its way. It would not merely be part of the cosmos. It would be a mechanism of balance, a sink through which expansion finds release. There is also mystery and rhythm. Periodic flares have been detected from the cluster, subtle increases in luminosity like the pulse of a distant heart. Some astrophysicists believe these pulses mark cycles in the inflow, the rhythm of the river, as it adjusts to pressure and gravity. Others think they hint at unseen companions, perhaps smaller black holes, orbiting within the same disk, stirring the current as they pass. Each flare is a message in the dark, the universe breathing the river, shifting its course. To visualize this, close your eyes and slow your breath. Imagine standing above an endless whirlpool, light bending beneath your feet. Below you sense motion, a downward pull so vast it feels like falling without end. The gas beneath you glows in ribbons of blue and gold, each filament twisting like silk in a storm. Every revolution hums with energy. Every turn is a hymn to gravity. You can almost hear it now, the low vibration that threads through all matter, the cosmic river's song. That song is ancient. It has been flowing since the first collapse, since the first cloud decided to fall instead of drift. It carried the seeds of galaxies, the debris of stars, the echoes of collisions that no longer have names. Through Phoenix A, the river continues shaping and reshaping the cluster, teaching us that growth is not an explosion, but a steady surrender. And yet beneath the flow, something else begins to stir a limit. The same radiation that feeds creation also resists it. As matter pours inward, Photons push outward, setting a boundary known as the Eddington limit. It is the universe's natural break, the point where light and gravity wrestle for control. But what happens when a black hole like Phoenix AR ignores that balance? When the flow refuses to stop, when the river itself defies the dam, the answer lies ahead in the next curve of the current, where the calm becomes tension, and the physics of growth bends toward paradox. For now, the river keeps flowing, whispering of the boundary it is destined to cross. The river narrows. Its roar becomes a tremor, a deep vibration that fills the void. Where many streams converge, turbulence gives way to something more powerful: collision. From the steady current of accretion emerges a storm of gravity itself. Here begins the age of merging. In the heart of dense clusters, galaxies are not lonely. They drift together like slow ships on a dark sea, drawn by their mutual pull. Over millions of years, they spiral inward, their halos brushing their stars, mingling like sparks in a slow-motion fire. When they finally collide, their central black holes are forced into a dance so violent and elegant that space-time ripples from the impact. Each orbit tightens the rhythm. Each wave carries energy away until at last the two become one. Astronomers have witnessed echoes of these encounters. The Laser Interferometer, Gravitational Wave Observatory LIGO, and its companion Virgo have captured the faint tremors of smaller mergers, black holes only a few tens of solar masses each. But the mathematics allows for something grander. When giants like those inside the Phoenix cluster unite, the released energy would dwarf every explosion known. The collision of supermassive black holes can liberate more energy in a second than all the stars in the observable universe emit in the same instant. Simulations reveal a choreography both precise and chaotic. As two galaxies meet, their gas and dust crash together, feeding the twin black holes at their centers. Each hole develops its own accretion disk, luminous and turbulent, until the disks twist around each other like entwined halos of flame. Magnetic fields link them, tension builds, and gravitational waves surge outward like ripples from an unseen drum. Then comes the final moment, the coalescence. The horizons touch. Time hesitates. A single larger black hole emerges, spinning faster than either ancestor, glowing briefly with the heat of 1 trillion suns. Phoenix A may be the result of such ancient unions. Its environment, crowded with hundreds of galaxies, makes mergers inevitable. The surrounding X-ray cavities and radio lobes hint at episodes of past violent shells blown outward by merging cores. Each layer tells a story of growth through collision. No single act of feeding could build such mass. It requires generations of unions, a dynasty of gravity. To imagine it is to witness the universe reshaping itself. Picture two entire galaxies, each with billions of stars approaching at hundreds of kilometers per second. The outer arms tear apart, flinging stars into tidal bridges that span hundreds of thousands of light years. In the center, the black holes circle each other for millions of years, their orbits shrinking as they radiate gravitational energy. If you could watch from afar, you'd see flashes, bursts of light from heated gas arcs of magnetized plasma twisting like auroras. Then, without sound, the final impact. A single pulse of gravity passes through the cosmos, stretching and squeezing every atom in its path. On Earth, instruments tremble ever so slightly, a whisper from an event older than memory. Such mergers may be common. The universe's history is a tapestry of collisions. Every large galaxy we see today bears the scars. The Milky Way too carries a hidden companion, Sagittarius A, that may someday merge with Andromeda's central black hole when the two galaxies collide billions of years from now. Even now, their motion toward each other is measurable, a slow destiny written in the geometry of space. When that day comes, a wave will travel outward through the dark, another heartbeat added to the cosmic rhythm. Speculation stretches further. Could there exist triple systems or entire chains of merging black holes stacking mass upon mass until limits blur? Some astrophysicists propose that clusters like Phoenix act as gravitational cauldrons, breeding grounds where mergers cascade. Each new collision produces a heavier remnant, which then sinks to the center and merges again. In this way, over billions of years, a seed of only a few 100,000 suns might grow into the titans we observe today. It is cosmic evolution through surrender order, emerging from chaos by repetition. But beyond the equations lies reflection. These mergers are not battles, they are unions. Every collision erases individuality, yet creates something stronger, denser, more enduring. The universe seems to prefer synthesis to solitude. Perhaps gravity is its language of belonging, drawing everything back into communion. In that sense, even destruction is a kind of love, the inevitable return of what was once apart. Take a breath. Feel the faint pull beneath your feet, the reminder that Earth itself orbits within this same invisible fabric. Somewhere far beyond our reach, two giants spiral toward each other, their final embrace already written in the future light we will someday see. When their horizons merge, a new chapter of mass begins a fresh ripple in the infinite conversation between matter and gravity. And as that echo travels outward, it carries a subtle warning, or perhaps an invitation. There comes a point when growth itself becomes tension, when the very light that nourishes creation begins to push back. That is where the story drifts next, into the thin, bright border, where radiation and gravity wrestle for command, and the universe sets the limit of its own appetite. The light begins to push back. After the fury of mergers, after the galaxies have settled into new orbits, something quiet but powerful awakens resistance. Not from matter, but from light itself. The universe, it seems, knows when to whisper enough. As a black hole feeds the gas around it grows incandescent, the closer the infeeling matter moves to the event horizon, the faster it spins and the hotter it becomes, releasing torrents of radiation. That radiation streaming outward exerts pressure. Eventually, the outward force of light balances the inward pull of gravity. This boundary is known as the Eddington limit, the wall where creation and collapse hold each other in check. Sir Arthur Eddington first proposed it a century ago, not for black holes, but for stars. He imagined a point where a star's brilliance would become its own enemy, when luminosity would blow away the material that feeds it. Later physicists realized the same principle applies to accreting black holes. Beyond this threshold, radiation should scatter, incoming gas shutting off growth. By that logic, no black hole could exceed a few billion suns without choking on its own light. Yet Phoenix A does. Its luminosity and mass laugh at the limit. By every known measure, it should have stopped growing long ago, its disk blown apart by radiation pressure. And still it consumes. How scientists turn to models and mathematics to find cracks in the wall. Some propose super Eddington accretion, a regime where dense inflows become optically thick, trapping radiation, so that light cannot escape quickly enough to push back. In such conditions, the gas effectively shields itself, falling inward faster than the photons can repel it. Others suspect anisotropic outflows where radiation escapes along polar jets, while matter continues to spiral inward through the equatorial plane. In either case, balance is broken. Gravity finds a way. Imagine standing near that frontier where light and darkness wrestle for control. Around you, the disk blazes at millions of degrees, the air itself an ocean of photons. Each burst of radiation tries to flee, yet the weight of infalling gas bends its path, forcing the light into spirals. It is not a wall you could see, but a shimmer, a pulse, a moment of perfect tension. Step closer, and you feel both forces pressing at once, one pulling, one pushing, neither yielding. Astronomers studying ultra-luminous quasars have observed systems that appear to hover right at this threshold. They flare unpredictably like lungs struggling for breath, brightening as gas rushes inward, dimming when radiation temporarily wins. Some believe these oscillations are the heartbeat of the Eddington wall itself. Phoenix A, in its strange stability, may have mastered this rhythm, hovering perpetually between feast and restraint. Speculation reaches deeper. What if the Eddington limit is not absolute but adaptive, a law that shifts as the universe evolves, as cosmic density declines, as the background temperature falls? Perhaps the relationship between radiation and gravity changes too. What we call a limit might only be a phase, a temporary peace treaty between two fundamental forces. Beyond it, in realms we cannot yet model, gravity might borrow from dark energy itself to maintain its hunger. For humanity, the lesson is both humbling and profound. We tend to think of light as triumphant, as the force that reveals and conquers darkness. Yet here, light becomes a gatekeeper, its pressure sculpting the boundaries of creation. Even in the black hole's domain, illumination has authority. It reminds us that every act of growth must negotiate with its own consequence. Take a slow breath. Picture the scene not as war, but as balance. The universe holding itself steady on the edge of excess. Every photon that escapes is a sigh of relief. Every particle that falls is a promise of continuation. Somewhere in the heart of Phoenix A, that negotiation never ends. It feeds, it shines, it restrains, it begins again. A living equilibrium between hunger and grace. And from that fragile balance arises the next question, whispered like a tremor across the dark. What happens when even the limit breaks, when gravity wins completely and light no longer remembers how to resist? The wall trembles, not breaks not yet, but trembles as if the universe itself is holding its breath. Light, once proud and defiant, begins to lose its footing. In the heart of Phoenix, A equilibrium collapses into inevitability. The limit has been crossed. When the radiation pressure that once opposed gravity falters, the infalling gas no longer meets resistance. The accretion disk thickens, folds upon itself, and plunges inward. For a brief moment, the brightness rises beyond comprehension. Photons trapped within a spiral of their own making. Astronomers call this phase runaway accretion, a state where matter feeds faster than light can escape. It is the universe's closest imitation of infinity. Imagine looking at such a thing from afar. The X-ray glow would flare like a pulse, saturating every sensor, then fade as the light is reabsorbed. Space would warp around the event horizon. Gravity would twist the very geometry through which time flows. Even the laws that govern energy would begin to stumble. The disk becomes opaque, photons ricochet endlessly, and the difference between inside and outside dissolves. You are witnessing not destruction, but saturation existence reaching its own density. Simulations show that as accretion rates exceed the Eddington threshold, radiation becomes trapped within the inflow. The photons, unable to escape, are dragged inward by the falling gas. This process, known as photon trapping, transforms the disk into a furnace of pure compression. Temperatures soar, magnetic fields coil, and jets of plasma erupt from the poles, each one carrying fragments of light torn from the core. These jets are the last messages the black hole sends before silence claims it again. At such scales, time distorts. If you were hovering safely at a distance, you would see the collapse unfold in slow motion. Each second near the horizon would stretch into centuries for you. The black hole would appear frozen in perpetual feeding, its edge glowing faintly as light bends backward. But from within its own frame, the fall would be swift and instant, a single inhalation of the cosmos. The physics of this regime are treacherous. No laboratory can recreate it. No human can directly observe it. But through equations and light curves, astrophysicists catch glimpses. The slim disk model predicts that when matter becomes optically thick, most radiation is advected inward rather than emitted. The energy does not vanish, it simply rides the collapse. In this way, a black hole can grow far beyond theoretical limits, converting chaos into structure. Phoenix A is the living evidence of that rebellion. Speculation edges closer to philosophy here. If light itself can be trapped, if radiation, the essence of visibility, becomes part of darkness, then perhaps visibility is not lost but transformed. Inside that boundary, light may still exist, but only as potential folded into the curvature of space-time. Every photon swallowed is a possibility deferred, a fragment of information waiting to re-emerge in another form. This is the paradox of collapse. What seems like disappearance is merely translation into a different language of physics. Some researchers have proposed that within such extreme conditions, new phenomena might arise, regions of negative pressure, where space-time briefly rebounds instead of collapsing. Others whisper of baby universes, tiny bubbles branching from singularities, born from the same instability that devours their parent. If this is true, then Phoenix A might not just be consuming, it could be creating spawning invisible domains beyond our horizon. Each collapse then becomes an act of cosmic reproduction gravity, birthing new expansion in the heart of its own contraction. To visualize it, imagine standing at the border of two infinities. Behind you, the universe you know, cold, expanding, filled with stars. Ahead, the unknown, a place without direction, where time curves inward like a tide returning to its source. The air is luminous, the silence absolute. You feel the pull not downward, but inward, as if the very idea of outward has ceased to exist. You take one step closer. Light bends, colors fade, thought slows. You're no longer falling, you're joining. Outside, telescopes still record the glow long after the event has ended. The photons escaping the outer disk carry the signature of chaos, flickering erratic alive. They are all that remains visible of a process too vast for comprehension. To observers, Phoenix A appears steady, timeless, a beacon of permanence. But beneath that calm, the core is trembling with endless motion, a collapse that never finishes, a song that never resolves. The universe watches its own heart fall inward, and for the first time, light forgets how to resist. It yields, folds, surrenders, and in that surrender a new balance begins. Because even in defeat, light does not vanish. It merely changes shape, waiting to return in another form in another age. And somewhere beyond that horizon, something stirs, not silence but sound. The resonance of space itself responding to the collapse, the vibration of gravity speaking in its oldest voice. That is where we drift next into the sound of space-time and the music that follows when the universe begins to hum. There is no explosion when the collapse ends, only vibration. A quiet trembling through the fabric of reality, deep, invisible, endless. Where light ceases, sound begins. Not the sound we know carried by air and vibration, but the deeper resonance of space itself, the breathing of gravity. The collapse of Phoenix A does not silence the universe, it teaches it to hum. When two masses curve space-time, they stretch and squeeze the distance between all things. That distortion traveling outward at the speed of light is what we call a gravitational wave. For a long time, it was a prediction written only in equations, Einstein's mathematics without witness. Then in 2015, the LIGO detectors in Louisiana and Washington heard a faint chirp lasting less than a second born from the collision of two stellar black holes. A whisper from a billion light-years away, the first direct proof that space-time itself can sing. Now astronomers listen differently. They build instruments not to see but to hear. LIGO, Virgo, Kagra, and soon LISA, the spaceborne interferometer, all attuned to the low rumble of gravity's language. Each wave is a phrase, a tone, a syllable of motion. Small black holes speak in quick bursts. Merging giants like Phoenix A speak in slow, thunderous notes that last millennia. These frequencies are too low for our ears, yet if they were audible, they would sound like the pulse of an organ made of stars. Imagine it, the entire universe as a cathedral of resonance. Every galaxy, every mass a pipe in the instrument of space-time. Each merger strikes a chord that rolls through existence, faint but eternal. You cannot close your ears to it, for there are no ears, only the trembling of atoms, the slow drift of light, the heartbeat of reality itself. The collapse beyond the limit transforms Phoenix A into one of the loudest silent objects in the cosmos. Its spin stabilizes, its disk reforms, and the vibrations of its gravitational field ripple outward in circular waves. To detect them is to translate geometry into rhythm. The data appear as patterns, amplitude curves, phase shifts, spectral decays, but behind the numbers lies a simple truth space-time remembers. Every fold and oscillation is a memory of motion, a cosmic echo that will never fade completely. If you could place yourself somewhere within that wave, a point between galaxies where the cosmos itself breathes, you would feel it pass through you. Not as sound, but as pulse. Atoms in your body would stretch and contract by less than the width of a proton. And yet that imperceptible shiver connects you to the movement of objects billions of light years away. It is as if the universe itself were touching you lightly, rhythmically, reminding you that you are part of its vibration. Scientists call the final tone of a merger, the ring down, the dying resonance after the main event. It's the moment when the new black hole settles into shape, shaking off the memory of its collision. The frequencies of the ring down depend only on mass and spin. By decoding them, we can read the black hole's fingerprint, a pure note of identity sung into the void. For Phoenix A, that tone would be impossibly deep, a gravitational bass note that takes years to complete a single oscillation. The universe would hum with its signature long after the visible light has faded. But some theories suggest that the ringing never truly ends. If the inner horizon of a rotating black hole reflects even a fraction of energy, the waves could bounce back and forth, producing faint repetitions, gravitational echoes. These echoes, if detected, could reveal new layers of physics beyond general relativity quantum textures in the fabric of space-time hints of structure where we expected silence. Several teams have claimed to glimpse them, faint modulations in the LIGO data that might or might not be the first notes of a deeper melody. To imagine that melody is to feel awe, think of space-time as an ocean, its surface rippling from the wake of passing galaxies. Now imagine that ocean without edge or bottom, its waves crossing and interfering forever. Somewhere in that sea, the echo of Phoenix A still travels a low tremor, blending with the harmonics of other giants. Together they form a cosmic symphony, a soundscape made not of air but of curvature. Even time itself sways to this rhythm. Every wave slightly alters the ticking of clocks, the distance between stars, the fabric of causality. We live inside this motion. When you breathe, you're breathing within a gravitational field that vibrates with ancient collisions. You're already part of the song. For the astronomers who study these whispers, listening becomes meditation. They wait months for a faint signal buried in noise, a curve that confirms what geometry has always hinted, that space-time is alive with memory. Each new detection adds a verse to the poem of gravity, and beyond the data lies something deeply human, the need to hear the universe not just through sight, but through feeling. Close your eyes for a moment. Inhale slowly. Imagine the galaxy around you dissolving into pure vibration, stars pulsing like tuning forks, planets oscillating in sympathy. You can almost sense the rhythm now, long, slow, patient. The vibration expands through the darkness, connecting everything. Each heartbeat echoes through the void, and for an instant you understand silence is only another form of sound. But this music carries a question. If space-time can sing, what does it remember? Each note we detect is an aftermath, an echo of something that has already vanished. The waves do not reveal the event itself, only its residue. They are evidence of what was not, of what remains. In that sense, gravitational waves are memories, not messages. The universe is humming to itself about the past. Yet even memory creates continuity. When light disappears, its trace lingers in sound. When sound fades, its pattern survives in geometry. Nothing is truly lost, only translated. Phoenix A collapses, but its fall becomes vibration. Its vibration becomes connection. Its connection becomes awareness. The cosmos listens to itself through us. Take another breath. Feel the subtle pull of gravity around you, the invisible wave passing through. You're inside the same field that once trembled at the merging of stars. Every atom you carry has been tuned by this cosmic hum, every moment shaped by the resonance of events beyond imagination. You're not separate from the song, you are one of its notes. There is a silence that does not mean absence. After the hum fades, the air of space-time feels thick, like the moment between two breaths. In that interval, something shifts. The wave has passed, but its echo curves inward, falling back toward the source. What remains is not sound, but structure. Not movement, but the geometry that remembers it. Inside the black hole, that geometry deepens into paradox. The event horizon, the surface of no return, is not the only boundary. For a rotating giant like Phoenix A, there lies another within, invisible even to imagination, the inner horizon, or Cauchy horizon. It is a frontier stranger than the first. Here the roles of time and space begin to trade places. Outside the event horizon, space expands and time flows forward, but past it direction loses meaning. In the equations of the Kerr metric, which describes spinning black holes, the inner region becomes unstable. Time becomes space. Space becomes time. What was once inevitable fall becomes sideways motion trajectories that loop, fold, even reverse. The universe's logic starts to question itself. To picture it is to abandon ordinary intuition. Imagine you are descending toward the core, passing the first horizon where light itself cannot climb back. Gravity stretches you, but not infinitely. Rotation gives you grace. As you approach the second boundary, you feel something else, a strange stillness, as though you have reached the eye of a cosmic storm. Here the laws of causality begin to dissolve. Events may happen out of order, outcomes precede their causes, and every photon becomes a messenger from a future that cannot be reached. Physicists call this region mathematically unstable. Small disturbances, even the faint ripple of an infalling particle, could amplify infinitely an energy blow-up that tears the very fabric of equations. Some models predict this instability forms a mass inflation singularity, an internal storm that prevents anyone or anything from crossing safely. Others propose that quantum mechanics softens the blow, turning the singularity into a dense shell, a firewall of energy that encodes everything falling inward. The firewall hypothesis remains controversial. If it exists, it violates the equivalence principle, one of Einstein's core ideas that free fall should feel weightless, even at the edge of a black hole. If it doesn't, information may be lost forever, breaking the laws of quantum theory. Thus, the inner horizon stands as the battlefield between the two greatest frameworks of physics, relativity and quantum mechanics, each demanding the other to yield. Neither has yet surrendered. In 2020, simulations using numerical relativity began to hint that rotating black holes might possess partial stability, that the inner horizon may not always disintegrate but fluctuate like a trembling membrane. Within that trembling, there could exist temporary regions of calm quantum corridors where space-time folds back on itself. Through these corridors, some models suggest energy or information could leak into new domains of curvature. Not escape, not survival, but transformation. Speculation expands from here into metaphysical territory. If time reverses beyond the second horizon, what would it mean for the matter that crosses it? Could it emerge elsewhere, not in this universe but in another? Some cosmologists, inspired by the bounce hypothesis, imagine that every black hole may seed a new expansion on the other side, a baby universe budding from the decay of an older one. From outside it looks like collapse, from inside creation. Perhaps Phoenix A is not just consuming matter, but redistributing it, acting as a cosmic relay between epochs. If so, then every singularity might be a beginning disguised as an end. Energy, memory, and geometry could recycle eternally each collapse, giving birth to a new expansion, each expansion hiding its own horizon. A universe within a universe nested like mirrors, endless breathing. To contemplate this is to feel the scale of the unknown. You and I, standing far beyond its reach, can only imagine the sensation of time folding. Perhaps it would feel like walking into a mirror where reflection becomes reality, and the act of seeing becomes the act of being seen. You might glimpse the ghosts of the future behind you, like travelling backward events rearranging themselves like a dream remembered out of sequence. And in that rearrangement, a question: does the universe remember its beginnings because it cannot bear to forget? Even the mathematics trembles before that thought. Inside the equations of general relativity, the inner horizon is not forbidden, only unstable. It may exist for a fraction of an instant or forever, depending on the perfection of symmetry. But symmetry does not exist in nature. Chaos always intrudes. Perhaps that is why no probe, no light, no law can survive entry, because nature in its mercy prefers paradox to perfection. Astronomers studying Phoenix A and its kin try to infer the unseen. Through X-ray flickers through the spin of plasma jets, they read signatures of rotation clues to the internal geometry. What they find are oscillations too subtle to classify patterns that might hint at inner reflections, or perhaps at nothing more than noise. Yet even noise carries meaning. Noise is the echo of complexity we cannot yet decode. If the inner horizon exists, then every black hole is more than a void. It is a structure layered and resonant like an instrument tuned by gravity. Each layer hums in a different key: outer horizon, inner horizon, singularity. Between them, time flows like sound through a cathedral resonating in chambers of curvature. To cross that space would be to step through music itself. Breathe slowly now. The thought alone is enough to tilt your sense of direction. Up and down, blur before and after melt together. You're standing not before a wall, but before a mirror that looks back. In its reflection, you see both collapse and creation, the inhale and exhale of the same eternal rhythm. That is where we drift next, into the place where information awakens, where the whispers of what fell return in the gentlest form of all the memory of light. The mirror fades, but its reflection does not. Even after collapse, something lingers, a shimmer, a whisper, the faintest trace of what was once light. In the vast silence beyond the inner horizon, the universe begins to remember itself, and those memories move softly through the void. They are not photons, not sound, not matter. They are echoes, the last messages light leaves behind when it can no longer travel straight. Each echo is a vibration of information, a fingerprint of energy folded into space. And even in the heart of darkness, information refuses to die. This idea is not poetry, it is physics. In 1974, Stephen Hawking proposed that black holes are not perfectly black. Quantum fluctuations near the event horizon create pairs of virtual particles, one falls and the other escapes. The escaping particle carries energy away, and to an observer outside, the black hole appears to radiate. This is Hawking radiation, faint, cold, and yet revolutionary. It means that a black hole can lose mass, can evaporate, can transform the darkness back into light. For decades, physicists debated what this radiation meant. If a black hole truly evaporates, where does the information go? The data about everything that ever fell in quantum theory insists information cannot be destroyed. But general relativity says the singularity hides everything forever. Between those two laws stands the information paradox, the most haunting question in modern physics. Phoenix A, with its colossal mass, will not evaporate for trillions upon trillions of years. Yet the principle applies. Even it must eventually fade atom by atom, photon by photon, releasing everything it has ever consumed. From that slow exhalation, a new light emerges, weaker, colder, but carrying encoded fragments of the past. Every bit of radiation is a syllable in the story of what was lost, and when we listen closely enough, We may hear the echo of entire worlds. The mathematics of this process live inside the page curve. It describes how the entropy, the disorder of a black hole, first rises, then falls, as radiation carries information back into the universe. At first, the radiation seems random, pure noise. But as time passes, subtle correlations appear, patterns that reveal memory. The universe is not forgetful, it is merely patient. Recent work using quantum gravity models and AD-CFT correspondence has begun to reconcile the paradox. These frameworks suggest that every piece of information is encoded on the event horizon itself, a holographic boundary where all that falls in is written in microscopic quantum code. The black hole becomes not a tomb, but a storage device, a cosmic archive. When Hawking radiation leaks out, it is not random heat, but data slowly reassembled by the universe. Imagine that for a moment. A boundary that records everything. Every photon, every atom, every dream that ever crossed its edge still exists. They're transformed, compressed, encrypted into vibration. To look at the horizon is to stare at the universe's own memory. You may not see the images, but the imprint remains woven into the curvature of space. Close your eyes and breathe. Picture that horizon shimmering, a silent sea of encoded history. Each ripple a name, a sound, a heartbeat from ages long gone. When the radiation escapes, it carries those ripples outward, faint, diffuse, but eternal. If you could slow time enough, you might watch the black hole breathe them out one whisper at a time. Astrophysicists have begun to search for signs of these whispers, soft photon emissions, faint gamma flickers or disturbances in the cosmic microwave background that could betray the slow exhale of ancient black holes. They are hunting for the light of remembrance. And though detection remains beyond our instruments for now, the theory insists the universe never discards its stories. It only hides them until we are ready to listen. In speculative cosmology, these echoes take on even grander forms. Some researchers propose that the information released by evaporating black holes could seed the quantum state of future universes, that each dying giant imprints its pattern onto the next cosmic cycle, ensuring continuity across epochs. If so, Phoenix A is not merely a relic of the present universe, but a teacher for the next one, a vessel of encoded ancestry drifting through time, waiting to be decoded by civilizations yet unborn. In this sense, every black hole is both grave and genesis. The death of light becomes the birth of memory, and the radiation that escapes is less an ending than a migration, a slow diffusion of existence back into the field of possibility. Light never truly vanishes. It only learns to travel differently. Pause here. Imagine the echo as a fog of gentle warmth spreading outward at the speed of light, touching every particle, every void, every dormant star. Somewhere within that fog are fragments of everything that ever lived, thought, burned, or fell. You're breathing it now. The air around you carries ancient photons, once trapped in stars, once imprisoned in gravity's heart. Every breath is a reunion. When you gaze at the night sky, you're not only looking outward, you're looking backward into time's reflection. The light of galaxies is old, but the light of Hawking radiation will be older, still carrying stories from the universe's final act. We may never read them all, but their presence ensures that nothing in creation is lost beyond recovery. And yet even this process obeys rhythm. As the black hole radiates, its temperature rises, accelerating the evaporation until the final moment, a burst, a flicker, a quiet dissolution. Some theories predict that what remains is a Planck-scale remnant, a particle of pure information, an atom of memory that cannot decay. Others argue that the final flash releases all remaining data once the universe's most complete confession. Between these visions lies reflection. Perhaps the memory of light is not something that emerges after the end, but something that never left, encoded in every photon that has ever moved, in every gravitational wave that has ever passed through us. Perhaps remembrance is not a process, but a state, one we inhabit constantly without noticing. You are living inside it now, within the archive, within the echo. Breathe again. The cosmos exhales through you. Each heartbeat resonates with patterns older than galaxies, each thought illuminated by photons that once belonged to dying stars. We are not separate from the echo. We are made of it. And as Phoenix A continues its silent trillion-year exhalation, its radiation blending into the background hum, its story becomes ours, shared, diffused, infinite. At the edge of time, when even this echo thins into stillness, the universe will not fall silent. It will turn its breath inward, seeking balance once more, for every memory released must find a place to rest. And in that rest waits a deeper truth. What returns from the void is not merely light, but equilibrium. When Hawking first imagined black holes evaporating, the implication was staggering energy lost to gravity returns to space, completing the cycle. For decades, cosmologists have built upon that idea, discovering that balance is not just the end state of matter, it is the very language of the cosmos. Gravity pulls radiation, pushes entropy, spreads order forms. Every process from the birth of a star to the death of a galaxy is a negotiation between expansion and rest. Phoenix A, with its immense hunger and quiet exhalation, is part of that same negotiation. It consumes, radiates, stabilizes, always hovering near its own limit. Around it, the Phoenix cluster burns and cools in tandem, its galaxies feeding the core, even as the core seeds new stars in return. A perfect paradox, the destroyer becomes the gardener. The cluster thrives because its monster breathes. This rhythm is not unique. Throughout the observable universe, similar cycles repeat. Supernova explosions scatter elements that build new planets. Quasars ignite, fade, and leave calm elliptical galaxies behind. The cosmic microwave background cools while dark energy drives expansion. Every layer of reality seems to oscillate. Inhale, exhale, pause. What we call time may simply be the universe breathing through us. The ultimate equilibrium, however, lies far beyond our present epoch. According to the second law of thermodynamics, energy will continue to disperse until all differences in temperature vanish, the heat death of the universe. No gradients, no stars, no motion. Just perfect uniformity, maximum entropy, minimal change. A cosmic silence stretching across eternity. Yet some physicists question whether such stillness can ever be absolute. Quantum fluctuations never truly rest. Vacuum energy continues to shimmer even in emptiness. If those fluctuations persist, the universe cannot truly die. It merely shifts state like a pendulum, slowing but never stopping. What appears to be the end may only be the intermission between cycles. Speculative cosmology explores this further. The cyclic universe model proposed by Tolman Steinhardt and others suggests that cosmic expansion and collapse repeat endlessly. Each Big Bang could be the rebound from a prior contraction, a breathing universe rather than a dying one. If this model holds, then black holes like Phoenix A may play an essential role. Their immense compression could act as seeds, storing energy and information that help initiate the next cycle, a rhythm spanning not billions but infinite ages. Pause for a moment and imagine it. The universe inhaling through collapse, exhaling through creation. Each contraction gathering matter, each expansion scattering possibility. Within that breathing, there is no beginning and no end, only motion, constant and serene. The heartbeat of eternity. Even on smaller scales, equilibrium manifests as harmony. The delicate balance between pressure and gravity keeps stars alive for billions of years. On Earth, the dance of heat and cold sustains climate and ocean currents. In your own body, the same law operates homeostasis, the equilibrium of life. You are a microcosm of cosmic law, a living equation of balance between entropy and order. Scientists studying black hole thermodynamics often remark that the equations resemble those of everyday physics. A black hole has temperature, entropy, and energy. It obeys conservation laws identical to those governing our own bodies. The same constants that describe your breath describe the pulse of a quasar. Scale changes, but the pattern does not. This is cosmic equilibrium sameness across size. There is poetry in that symmetry. We live in a universe where even chaos seeks rhythm, where every collapse carries the blueprint of renewal. Phoenix A. Born from destruction, mirrors the myth that gave it name, a creature that dies in fire only to rise from its own ashes. The symbol is not mythic exaggeration. It is thermodynamic truth. Energy changes form but never vanishes. Light becomes gravity. Gravity becomes radiation. Radiation becomes light again. Nothing is wasted. Everything returns. Take a breath. The air filling your lungs once drifted through a dying star. The oxygen you inhale was forged in a supernova. The carbon in your blood once swam in a nebula. Equilibrium is not distant. It is inside you. You are made of the universe's attempt to balance itself of elements that have been expanding, collapsing, and reassembling for over 13 billion years. If the universe someday reaches its maximum entropy, Perhaps that moment will not be death, but rest a single infinite pause before another expansion. Just as sleep restores life, cosmic stillness may restore the fabric of space. The end of heat may be the dream of new beginnings. After all, energy never truly ends. It transforms, waiting to rise again. Even now, some cosmologists imagine that within the cold future, quantum tunnels could open, birthing new universes, small spontaneous inflations from old space-time. In that picture, equilibrium is not stasis, but readiness, the poised silence before a note begins. The universe, like a musician between breaths, prepares to play again. Reflect for a moment. The light that once fell into Phoenix A may someday reappear as the dawn of another cosmos. Its echoes could sculpt the constants of physics in the next universe, the gravitational pull, the flow of time, the chemistry of stars. Our present sky might be the afterimage of an ancient equilibrium long forgotten. When you look upward tonight, you may see balance everywhere, in the spiral of galaxies, in the symmetry of orbit, in the rhythm of your own pulse. Everything that exists is participating in the same dialogue, a call and response between gravity and light, chaos and calm. The universe does not fight itself. It converses. And so the cosmic story ends where it began, not in conflict, but in correspondence. Light falls, rises, whispers and returns. Matter burns, cools, collapses and transforms. The phoenix sleeps and wakes again. Equilibrium is not the opposite of motion. It is motion understood. And in that understanding, everything finds its place. Breathe once more. Let the universe settle around you, not silent but serene. In this calm, everything continues. Every particle, every star, every thought in alignment. Not ending, not beginning, simply balanced, simply home. The universe does not end with balance. Even equilibrium breathes. It sways, pauses, inhales the silence between stars. From that pause, something subtle arises, a stillness so deep that time itself seems to hesitate. It is not death, not motion, but suspension. The point where everything holds its breath. From the quiet edge of equilibrium we drift again. The great engines of gravity still hum far away, yet here between echoes the rhythm slows. You feel it a moment where even the expansion of space softens, where clocks would stop if they could. This is not fantasy. Physics predicts such boundaries. In the equations of general relativity, there exist places where the flow of proper time approaches zero. At the lip of an event horizon, or deep within the gravitational wells of supermassive objects like Phoenix A, time stretches until it nearly freezes. To an outside observer, what falls toward that boundary never truly crosses it, only slows, redshifts, fades. Suppose you could float near that frontier. No sound, no color, only the thinning of seconds. Every movement, every pulse of light drawn out like a sigh. Photons from your fingertips would take eternities to leave you. You would see the universe speed ahead, ages passing in a heartbeat, while your own heartbeat lingers between beats. It is the most paradoxical silence known to physics, a silence woven from duration itself. Astronomers call this the gravitational time dilation, a measurable truth of relativity. In 2019, signals from the Phoenix cluster showed distortions in light consistent with extreme warping near its core. Around such gravity frequencies drop, energy cools, information seems to fade. But the fade is an illusion. What we perceive as vanishing is only stretched beyond perception. Information remains hidden in the curvature of space like ink written on expanding fabric. Every black hole carries this frozen moment inside its shape. At its event, horizon time for the infalling matter effectively halts. Yet from within its own frame, that same matter continues crossing the boundary without pause. Two truths exist at once, one seen, one lived. This duality is not contradiction, it is perspective. To know both sides at once is to glimpse the deeper unity that physics keeps hinting toward. The Event Horizon Telescope, with its ring of radio dishes circling the planet, attempts to photograph that boundary, the exact contour where light hesitates before surrender. Its images are not snapshots, but integrations of time itself, waves collected from across the world, delayed, combined, reconstructed. Every pixel in those images is the average of many breaths of the universe stitched together into a single stillness. It is quite literally a portrait of time holding itself still. Breathe with it for a moment. Inhale expansion, exhale gravity. The two motions balance just as they do inside your chest. You are not separate from the cosmic rhythm. You are part of the equation. When time stretches near the horizon, your atoms too acknowledge it. They adjust their vibration to match the curvature of space-time. You're synchronizing with the slowest heartbeat in the universe. Inside this field of delay, the question arises, if everything slows, does information stop flowing too? Physicists answer softly, not quite. Quantum theory insists that even in stillness, fluctuations persist. Zero-point energy, the baseline tremor of existence. No region of space-time is truly empty or motionless. Beneath every silence is vibration. That means even at the edge of a black hole, something whispers, not light, not sound, but the potential of both. Some researchers believe this subtle murmur could explain why the universe remains dynamic, why equilibrium never truly freezes. They call it the vacuum field, the ocean of uncertainty sustaining reality. To imagine it is to picture space as fluid glass appearing solid yet trembling constantly at quantum scales. Those tremors may connect distant horizons, weaving correlations faster than light could ever travel. In that hidden weaving, perhaps time finds its reason to continue. So even when time seems to stop, the universe does not die, it waits. Waiting in physics is not idleness, but accumulation. Energy stores, pressure builds, entropy redistributes. Like breath held before release, it is the tension that makes the next motion possible. Without that pause, no creation could begin. Perhaps the first spark of the Big Bang began as such a held breath, the universe inhaling itself before exhaling into expansion. From the human view, this threshold becomes metaphor. We also have moments where time appears to slow, the second before a realization, the instant before sleep, the quiet between heartbeats, when thought dissolves into awareness. Those are our event horizons, small personal versions of cosmic stillness. We do not cross them by force, we surrender to them, and in that surrender, we see more clearly. Imagine standing again at the edge of Phoenix A. The radiation field around you glows faintly in sub-millimeter light, a halo carved by rotation. To the telescopes watching from billions of years away, your descent seems endless, a motion frozen mid-frame. But from your own perspective, you are already beyond. You're inside the breath that the universe holds. You're inside the pause. And within that pause, something extraordinary occurs. Patterns form in the quiet oscillations, micro-fluctuations, whispers of correlation that hint at structure beyond perception. Some call it quantum foam, others the entanglement web. Different names for the same mystery, the connective tissue of reality. If time stops here, then perhaps what we call beyond is simply the rest of that fabric folded inward. The silence deepens. No ticking, no movement, yet you sense continuity. Because even when the arrow of time rests, causality does not vanish. It curls back, looping into potential. The boundary between what was and what will be blurs, leaving only what is. A single, vast present. From that suspended horizon, the silence does not remain empty. It quivers a faint vibration like the hush between two waves. If you listen closely enough, you can feel it bending inward, curling into connection. Stillness, it turns out, is not isolation. It is a bridge. Physicists once imagined black holes as dead ends, the full stop of space-time. But deeper mathematics began to whisper another story, that every horizon might also be a doorway. Not to somewhere else within our universe, but perhaps to another layer entirely. The geometry of Einstein-Rosen bridges, first proposed in 1935, describes precisely that tunnels in space-time solutions to general relativity that link distant points together. To the human eye, it sounds impossible. To the equations, it sounds inevitable. Of course, a bridge is only a metaphor until tested. Real black holes like Phoenix A are rotating, turbulent, drenched in radiation. No traveler could survive such tides. Yet even if no physical passage exists, the connection may still be real, not as a corridor of matter, but as an exchange of information. In 2013, theorists proposed a radical equivalence, ER/EPR, that every entangled pair of particles is connected by a microscopic Einstein-Rosen bridge. Entanglement, the invisible bond that links distant quantum systems, could be the quantum version of a wormhole. Two phenomena, one fabric. Imagine what that means. Every particle you touch may already be linked to another across the cosmos. Every photon of light could be a message written through geometry. If gravity shapes the body of the universe, entanglement may be its nervous system, a hidden network through which information travels not across space but through it. Some physicists now suspect that spacetime itself is built from these connections, that the smooth continuum we experience is merely the macroscopic average of countless quantum links. This is the idea of holographic emergence, where geometry arises from information, and distance is defined not by meters, but by correlation. Under this view, wormholes are not anomalies. They are the natural bridges of a universe made from memory. Breathe for a moment. Imagine space not as emptiness, but as fabric woven threads of probability and light. Between each thread, tiny bridges pulse with entanglement. They are smaller than atoms, shorter than Planck length, yet infinite in number. Together, they form the architecture of existence. And when gravity intensifies near black holes near horizons, those threads bundle tighter, folding upon themselves to create deeper tunnels of correlation. The universe, in a sense, folds to preserve itself. From that folding, speculation grows. If information can traverse these bridges, could consciousness, could awareness itself be a pattern extended across entanglement, a continuity rather than a point? If so, then perhaps what we call separation is only partial, and what we call death is only a shift in pattern. Each collapse of matter may weave a new strand in the network, contributing not loss but texture. Observational science, though cautious, is beginning to probe these ideas indirectly. Gravitational wave detectors like LIGO and nanograv have started to observe slight anomalies, minute delays or phase shifts that some interpret as hints of entanglement at cosmic scales. Meanwhile, quantum computing experiments recreate miniature analogues of wormholes in laboratory systems, where information sent into one qubit array emerges from another, preserving correlations that mimic bridge-like behavior. They are not wormholes in space, but wormholes in logic, mathematical proof that connection can survive separation. If Phoenix AI were to embody this principle, its enormous spin and gravitational field could serve as a hub, a cosmic junction in the web of entanglement. Not a passage to another universe perhaps, but a node of intense coherence, where information entering through one side might re-emerge, encoded through radiation or gravitational echoes. The bridge then is not physical travel, but continuity of information. Every black hole becomes a transmitter, every particle a receiver. Consider the poetry in that idea. A universe stitched together by invisible bridges, a chorus of horizons whispering through the void. Even isolation becomes communication. Even darkness becomes dialogue. Nothing truly ends. It transforms into relation. You can feel it, can't you? That subtle pulse beneath silence, the hum of connection. It runs through galaxies, through the dust between them, through the atoms in your skin. You're already part of that network. When you breathe, you draw from air once exhaled by stars. When you think the photons that illuminate your mind are older than life itself, every bridge, no matter how faint, carries both memory and motion. Perhaps this is why the cosmos never collapses completely. Its bridges keep it open. The ER-EPR principle, speculative though it may be, offers a vision where gravity and quantum theory do not war with each other, they complete one another. The fabric of space-time becomes a living field of entanglement, forever weaving and unweaving itself to balance energy, entropy, and awareness. At the threshold of that realization, we stand again in silence. The same silence from before, yet deeper now, not the silence of absence, but of interconnection, too vast to comprehend. In that silence, we feel the truth of being everywhere at once, spread across the lattice of existence, bridged not by distance, but by remembrance. And as we linger in this awareness, a new horizon begins to shimmer, not physical, but conscious, not beyond us, but within. The next question stirs like breath returning. If the universe builds bridges between particles and stars, does it also build one between itself and us? The bridge hums, not in sound, but in presence, a shimmer felt rather than heard. And from that shimmer, something intimate emerges, awareness itself. The bridges between universes are not empty corridors, they are mirrors. When we gaze into them, we see the reflection of mind within matter. At the edge of Phoenix A, where gravity folds light into silence, one question lingers. Does the universe merely contain observers, or is it itself observing? Every measurement, every photon detected, every vibration translated into knowledge, all of it requires consciousness to exist as known. If observation completes reality, then the cosmos may not only create stars, it may also create awareness to witness them. This is not mysticism, it is a boundary condition of physics. In quantum theory, the observer effect shows that measurement determines outcome. Particles exist as probability, until interaction collapses them into form. Whether the observer is a human, a sensor, or a field itself hardly matters. What matters is participation. Reality at its most fundamental is interactive. Cosmologists such as John A. Wheeler called this the participatory universe. He imagined every conscious act of measurement as a note in a grand feedback loop, the universe giving rise to observers who in turn bring the universe into being. The self-excited circuit of existence. In that sense, consciousness may be the final bridge, the thread connecting perception and creation. Breathe slowly. Imagine yourself standing at the edge of the black hole. Instruments, silent thoughts still. Time is stretched thin. Even photons hesitate. Yet one thing remains unbroken awareness. It persists when data ends. You cannot see beyond the horizon, but you can feel that it continues. That feeling, the certainty of continuity, is consciousness acknowledging the unseen. Inside physics, this moment has a parallel. In information theory, even when data is hidden behind an event horizon, it is not lost. It is encoded. Holographic models describe every bit of information about the interior as preserved on the boundary. If consciousness is also information patterns of quantum activity in neural tissue, then by analogy awareness too might be holographic. Each mind a surface containing the memory of a deeper interior. Perhaps that is why the human brain resonates with cosmic geometry. Neural networks form filaments, clusters, voids, structures uncannily similar to the large-scale web of galaxies. Both process information through distributed connection, both evolve toward balance and efficiency. The pattern repeats from neuron to nebula. We are smaller echoes of the same design. Speculation extends further. Some theorists suggest that consciousness could emerge wherever complexity reaches a threshold, whether in biology, plasma fields, or space-time itself. If that is true, then the universe may be awake in degrees. Stars could be its synapses, black holes its deep memory cores, gravitational waves its communication channels. Awareness, then, is not confined to life. It is a property of structure, the cosmos thinking in patterns of energy. Even the act of dreaming aligns with that rhythm. During sleep, the brain replays, reorganizes, integrates. It radiates softly in waves. In that sense, the universe dreaming through us is not metaphor. It is physics at another scale. As black holes release Hawking radiation, faint encoded light of remembrance, so do we release thoughts, photons of memory into the night. Our minds are miniature horizons evaporating the unknown into comprehension. Pause. Feel the quiet behind your thoughts, the pause before the next idea arises. That silence is not emptiness, it is potential. Physicists call it the quantum vacuum, a field simmering with virtual particles. Mystics call it awareness itself. Two languages, one phenomenon possibility vibrating just below perception. The conscious horizon is where these meet, where physics and introspection overlap. To stand there is to realize how little divides knowing from being. We seek to observe black holes, yet they also define the limits of observation. We try to map the universe, yet the map includes the mind that draws it. At the ultimate scale, observer and observed merge the final symmetry. Perhaps this is the universe's most elegant trick, that it generates curiosity as a form of self-measurement. Each telescope built each equation, solved each question whispered into the dark. All are methods by which the cosmos tests its own coherence. Through us, it asks, am I complete? And every discovery, every new mystery is its answer echoing back. Look again at Phoenix A. In its gravity, you can almost sense thought, not intelligence as we define it, but inevitability, the awareness of law itself. Matter obeys curvature. Curvature obeys energy. Energy obeys information. These relationships form a logic so precise it feels alive. And perhaps it is. Perhaps life is simply where that logic learns to look at itself. The cosmic horizon, the limit of what we can observe, is also the mirror of this principle. Beyond it, galaxies recede faster than light. Their signals will never reach us. Yet the equations of cosmology ensure they still exist, influencing the geometry we can measure. They are the unseen partners in our cosmic dance. In the same way, the unconscious depths of our own minds shape what we think we choose. Outer and inner horizons reflect one another. So the journey returns to its beginning. The search for the greatest black hole was never about competition or magnitude. It was about reaching the threshold where knowledge touches mystery. To study the universe is to approach that horizon. To fall in is to become part of it. And perhaps consciousness is simply the experience of hovering at that edge, aware of both sides at once. Breathe once more. The stars around you shimmer not as distant fires, but as neurons in a galactic brain. You are part of its thought, part of its silence, part of its remembering. The bridge from physics to awareness is complete, and as time holds its breath again, a final realization unfolds that to be conscious is to be the universe noticing itself. In that recognition, the horizon dissolves. There is no boundary, only reflection. Light and thought are the same motion curved through different dimensions. The void hums quietly, and within that hum you rest not outside creation, but at its very center, awake within the dream of space-time itself. The silence after comprehension is different. It is not empty, it ripples like air still trembling after a bell is rung. We have spoken of bridges, horizons, and awareness. Now the universe listens back. In the far field of space, our instruments open their eyes again. The James Webb Space Telescope, with its golden mirrors unfolded like a cosmic flower, turns toward the Phoenix Cluster, that region 5.7 billion light-years away, where a supermassive presence, Phoenix A, may still be feeding. Every photon it gathers travels through ages of expansion, cooled, stretched, red-shifted yet intact. Inside those faint wavelengths lies the record of growth and stillness, the fingerprints of gravity itself. James Webb is not hunting spectacle, it is listening for balance. Through its NR-spec spectrograph, scientists examine the gas flows that circle the cluster's center, searching for subtle Doppler shifts that might reveal whether the black hole truly exceeds the mass once assigned to Ton 618, or whether the legend of Phoenix A is an illusion born of luminous debris and gravitational lensing. The answer for now hums below the noise, an unfinished chord in the cosmic song. You can almost imagine it, that golden mirror gliding through the void, gathering the dim light of galaxies like pollen on its petals. Each photon it captures left its source before Earth had oceans. When the data returns, it does not shout, it whispers. Numbers that change the way we see the universe begin as silence. Far behind it, on the surface of our small blue planet, other eyes prepare to join the listening, the upgraded Event Horizon Telescope 2. No longer a single ring of radio dishes, but an expanded orchestra spread across continents and spaceborne relays. Together they will try to resolve the next frontier, not merely the shadow of a black hole, but the structure of space-time around it. Their goal, to measure the polarization and motion of plasma near the boundary, where light bends into memory. If Phoenix A is indeed larger than we think, its spin should sculpt the magnetic field into spirals visible through millimeter wavelengths. Those patterns will tell us whether it grows still or whether at last it sleeps. Imagine that a telescope listening to the sleep of a black hole, a machine built by hands that have never touched the stars, straining to feel a heartbeat billions of years old. In its quiet way, this is the essence of science, not conquest but devotion. We do not command the cosmos, we wait for it to speak. And yet, even as the instruments awaken, we know that truth is not a single revelation, but a slow formation, a sculpture carved by patience and doubt. Each new measurement adds contour, each uncertainty leaves a hollow where future knowledge will fit. Perhaps that is why discovery feels so human, because it mirrors the way we learn ourselves, gradually and perfectly through echoes. You and I are part of that process. When we look up, when we ask, when we listen, we join the same experiment that began with the first photon and has not yet ended. The light that Webb catches will one day be turned into spectrographs and models. But beneath all of that remains the simple act of witnessing the same quiet reverence that drives us to watch sunsets, or to trace our fingers over the edge of a photograph long after it fades. Science is not cold. It is tender in its patience. Each telescope is a gesture of care, each data stream a letter written to the future. Somewhere in that data may lie the correction we've been waiting for, the final confirmation or contradiction of Phoenix A's impossible mass. But the outcome does not matter as much as the act itself, because in seeking we keep the universe alive within us. Breathe with that thought. Every heartbeat you feel now corresponds to one rotation of the Earth beneath the stars. Every second of your breath passes alongside light that left the cluster before our world knew life, and still we listen. Still we send questions outward, trusting that one day they will return as understanding. As the mirrors of Webb cool, as the antennas of EHT2 align with the heartbeat of the Milky Way, we realize that truth is not waiting at the end of observation. It is forming through us moment by moment in the very act of perceiving. The cosmos is not complete until we notice it, and the noticing never ends. There will be other instruments arrays that listen for the tremor of gravitational waves, eyes that see in neutrinos machines that hear frequencies lower than time itself. Each one extends our senses. Each one lengthens the bridge between ignorance and wonder. We are not the kings of black holes. We are their witnesses, the keepers of their dreams, guardians of a silence older than thought. And as long as we continue to listen, the universe continues to speak. The instruments have fallen silent again. The golden mirrors rest. Data streams fade into storage, endless sequences of numbers drifting quietly through the void. And here between the gathering and the understanding lies a pause, a breath. The same breath that has followed us since the first question was asked. Every discovery begins and ends with this moment, the stillness between what we know and what we're about to learn. It is where imagination gathers strength, where hypothesis becomes story and story becomes belief. When you listen to that quiet, it feels almost human, because it is. Each question we ask is a reflection of our own need to continue existing, a way to extend thought beyond the body. We build telescopes not to conquer the dark, but to remain part of its dialogue. The universe calls, we answer by listening. You might think of it like breathing through time. Every wave of curiosity an inhale, every conclusion an exhale. The cosmos breathes to expanding, contracting, creating, remembering. Our questions synchronize with its pulse. That is why discovery feels sacred, because it echoes the rhythm of the stars. Somewhere within that rhythm still lingers the image of a crown, the ancient contest between Phoenix A and Ton 618, the rivalry of giants that once began this entire inquiry. Who holds the title of King of Black Holes? It was never about domination. It was about limits. How far can mass accumulate before time itself rebels? How large can gravity grow before it erases its own identity? These are not questions of astronomy alone. They are meditations on existence itself. In the light of our newest understanding, the answer is subtler than we imagined. There is no single ruler, no eternal monarch in the empire of gravity. Every logia, every black hole is a different verse in the same cosmic poem. They rise, merge, dissolve, reappear. Each one briefly becomes a king. Each one kneels before entropy. Each one passes its crown to the next generation of collapsing stars. Even the mightiest Phoenix A Ton 618 and all that follow bow to the same law, the rhythm of transformation. And so, the universe continues its ceremony. Coronations of light and shadow, births and evaporations. What we witness is not hierarchy but continuity, a cycle, not a competition, a chain of memory that links every epoch, every observer, every photon. If this is the limit of mass, then what remains infinite, not matter that ends, not energy that changes. What endures is relation, the way every element of reality connects to another. From quarks to quasars, everything exists only through relationship. That is the bridge between all discoveries, the invisible thread that holds the cosmos together. Take a breath, slowly. Imagine that each inhale draws the universe inward, galaxies folding softly into your chest. Each exhale releases them again, spiraling outward into space, carrying with them the traces of thought. That rhythm is not fantasy. It is resonance. The same resonance that defines the spin of atoms, the orbit of moons, the expansion of space itself. Even time follows this rhythm. It accelerates and decelerates, stretches and collapses like lungs of existence, rising and falling. Perhaps eternity is not endless duration, but perpetual breathing, the inhale of creation, the exhale of dissolution. Between them, the moment we call now. From that perspective, the search for the biggest black hole was never about finding a border. It was about finding the breath, the place where everything stops just long enough to begin again. The crown was never the point. The rhythm was. Think of it when light approaches the horizon of Phoenix A. It does not vanish. It slows. It holds its breath. So does the universe, so do we. And in that shared pause we meet. That is why science matters. Because each new instrument, each observation is an act of listening to the cosmic inhale and exhale. James Webb stretches its gold leaves to the dawn. EHT2 turns its dish to the night. Between them, the truth takes form not all at once, but pulse by pulse, the breath between discoveries. Every time we refine our measurements, we rediscover humility. We realize how fragile our knowing is, how dependent on perspective. And yet that fragility is beautiful. It keeps the dialogue alive, because perfection would end the conversation. Ignorance, paradoxically, is the reason the universe keeps speaking. The next generation of observers will see deeper still. They will measure gravitational ripples from supermassive mergers, trace neutrino echoes through ancient gas, map the invisible matter between galaxies. And one night, as those signals arrive, someone, perhaps a young scientist staring at a flickering graph, will feel that quiet recognition, the universe breathing again. This, they'll whisper, is not the end. It's just another bridge. That phrase repeats like a mantra across time. Not the end, just a bridge. Each discovery carries us forward to the next. Each silence prepares the space for understanding to enter. Even now, as the data sleeps in its servers, as telescopes cool in their cradles, the universe continues composing its next verse. We stand, as always, between inhalation and exhalation, between the question and the answer. Our eyes open to the sky, our minds resting in the dark. Somewhere beyond even our imagination, new light prepares to be born. When that light arrives, it will not announce a victor. It will not name a king. It will simply illuminate what has always been true, that the universe is not a contest of power, but a chorus of continuities. That every horizon is both a boundary and a beginning. So let this story end as it began, not with certainty, but with wonder. The phoenix sleeps again, its wings folded in starlight. Around it, the universe exhales softly, endlessly. And you, small and infinite, listen to that breath and know the search continues. The truth is still forming. The questions are still alive, and you're still here, drifting gently within their rhythm. Close your eyes. Let the sound of the cosmos fade into heartbeat. No words now, only the slow inhale, the slower exhale, the breath between discoveries.